All right, so here we have a fluid problem that involves Bernoulli's law. It's a container of water. We have this tank of water here that's filled up to a height h, and then there's a hole put in the side of this tank, and we're not given the exact size of the hole. We're just told that it's a small hole and that it's 6 meters up from the ground. And then water shoots out of the hole and travels 6 meters horizontally and hits the ground. So from this information, the first thing we're asked to find is the velocity of the water as it flows out of the hole in the side of the tank. So this is a projectile motion problem. It actually has nothing to do with fluids. This could be a ball being thrown horizontally from a height of 6 meters, landing 6 meters away from where it was thrown. It doesn't necessarily have to be water, but we're going to use projectile motion, which is kinematics, the motion equations, to solve for the velocity of the water as it exits this hole. So I'm going to put a vector here to represent the velocity of the water as it leaves the opening, and this is an x velocity. We are looking for Vx initial. And since the water leaves horizontally only in the x direction, we know that Vy initial is 0. There is no y velocity initial because the water leaves only in the x direction. All right, the other thing we know is as the water flies through the air, the x velocity remains constant. And another way of saying that is that the acceleration in the x is 0. Constant velocity is 0 acceleration. So this is all stuff that we learned back when we did projectile motion. There's no acceleration in the x. Now there is a y acceleration. The starting y velocity is 0, and then that y velocity gets bigger. So if we look at the water right here, it's now traveling downward, and then here it's traveling downward with an even bigger velocity, so I drew that longer. And the reason the velocity changes in the y direction is because we have an acceleration in the y, which we know to be gravity, which is negative 9.8. Okay, all right, so this 6 is our x displacement. This 6 up here is our y displacement, and that's negative. It's going to be a negative 6 because the water is going down vertically. Remember, our sign convention is plus, minus, plus to the right, minus to the left, up plus, down minus. So this 6 meters is negative, the vertical, because the water goes down. Okay, so the first thing we're going to do is we're going to find the time in the air. How much time, if we looked at one drop of water leaving this hole, how much time would that one drop of water take to reach the ground? We only have enough information to use the y direction to solve that. So the motion equation that works nicely here is y equals 1/2 gt squared plus Vy initial t. That's just the first kinematic on my list of kinematics written for the y direction. So the acceleration in the y is g, so I just put g there. Now when the water leaves the hole, there is no y velocity initial, so we can cross this out, and then we're left with this part, just y equals 1/2 gt squared, and we can solve that for t, which gives square root 2y over g. We plug the numbers in. Y is negative 6 meters, and then gravity is negative 9.8. So the time comes out as 1.1066 seconds. That's the time in the air. So now that we have time in the air, we can solve for Vx, which is what the first question is asking for, the velocity of the water as it leaves the hole. So again, the first kinematic, I'm going to write it for the x direction, 1/2 a t squared, where that's an x acceleration, plus Vx initial t. There is no acceleration in the x, so this first part of the equation goes to 0. So we're left with x equals Vxt. Vx is x over t. where x is the horizontal displacement, which is also 6 meters. And then we now know the time, 1.1066 seconds. So this gives the answer to the first question, which I'm going to round to the hundredths place, 5.42 meter per second. Okay, now the second question is Bernoulli's law, and we're going to use the answer from the first question. So I'm going to clean this up here a little bit. Clean this all up. Okay, the second question is asking us to find what this H is. How high is the water in the tank measured all the way from the bottom? Well, if we look at this, we already know the height for this part. This part right here is 6 meters. So really what we're looking for in this problem is this other height here. This is the height that we're trying to solve for, from the hole up to the top of the water. And then whatever that height is, we're just going to add the 6 meters. Okay, so let's write out Bernoulli's equation. This problem is solved with Bernoulli's law. Pressure 1 plus 1/2 density velocity 1 squared plus density gravity vertical height 1 equals P2. Okay, so here's Bernoulli's equation. Now, let's talk about y1 and y2. The only time that the dgy, this part and this part, the only time this becomes important is if there's some sort of vertical height involved in the problem, which we have here. So in general, y1 will always be 0. This y1 right here is going to be 0. It's like, you just think of it like a 0 point. So what we're going to do is we're going to set this level, the level of the hole, we're going to set this as y1. y1 equals 0. Okay, so if this is y1, that means that this velocity, the velocity of the fluid at this level exiting the hole, is going to be v1. v1 corresponds to y1. Okay, V1, we found it out to be 5.42 meter per second. And then the other thing is we know that P1, the pressure on the fluid, P1, as the water exits this hole, it's open to the atmosphere. The hole is open to the atmosphere, and whenever that's the case, the pressure on the fluid is the pressure of the atmosphere. So this is 1 ATM, 1 atmosphere, which we want to put into pascals. 101,300 pascals. That's the pressure of the atmosphere, of 1 atmosphere. Okay, whenever you're doing the Bernoulli equation, pressure has to be in pascals. All right, so we have Y1 set to 0, we have V1, and we have P1, the pressure on the fluid as it exits the hole. And I'll mention here a great way to think of this problem. A great way to think about this is like, it's almost like you have the beaker going like this. So this is Y1 down here, here's Y1, this is V1. So imagine this container just kind of like going like this. Okay, so we got V1 and then P1. All right. Now up here is going to be y2. This level up here is y2, and that's what we're solving for. Basically, we want to solve for this vertical height, which is y2. If we can find out y2, then we add that to the 6 meters, and then we know the total height of the water. Okay, so up here is y2. Now the velocity that corresponds to that is v2. Now, if you look at this situation, the water level in the tank is going to be coming down at an extremely small velocity. V2 is a very small velocity compared to V1. This water level is going to be coming down at an incredibly slow rate, whereas V1 is 5.4 meters per second. So looking at the Bernoulli equation, what we're saying here is that V2, this velocity, is so small compared to V1 that we're just going to set this to 0. And we can definitely do that because if you look at the equation, these velocities are squared. So there's a gigantic difference between velocity 1 and velocity 2, and when you square those velocities, the difference becomes even more remarkable. So V2 gets set to 0 because the velocity of this water level dropping is incredibly small. So V2 basically gets set to 0. Okay, and then the other thing is P2. So the pressure on the fluid up here is P2. Now, this is also open to the atmosphere, so the pressure up here is 1 atm, which is 101,300 pascals. But if you notice, the pressure down here at P1, at region 1, is also 1 atmosphere. So looking at the Bernoulli equation, P1 and P2 are identical, so they cancel out. P1 and P2 are the same, so they drop out. So the Bernoulli equation has reduced to 1/2 dV1 squared equals dgy2. Density drops out, densities on both sides, and we end up with y2 equal to v1 squared over 2g. So y2 is going to be 5.42 meter per second squared divided by 2 times 9.8, which gives an answer of 1.5 meters. So the total height of the water is going to be this 1.5 meter, so we figured out what this was, added to the 6, which gives us 7.5. So just in summation, the two key things to recognize in a problem like this is that the pressure on the fluid at region 1 is the pressure of the atmosphere, because this hole is open to the atmosphere. The pressure on the fluid up here at the top of the beaker or the tank is also the pressure of the atmosphere, because this is open to the atmosphere. So these pressures dropped out. And then the other thing was recognizing that this velocity, the velocity of the fluid up here at region 2 at the top of the tank, the fluid up here is moving so slow compared to V1 that we set V2 to 0.